Hey everyone, today let's try to solve another LeetCode problem. Today's problem is called apply operation to maximize score, which is a hard problem. So in this problem, you are given an array nums and also an integer k. So initially you start with a score of 1, and then you can apply the following operation at both k times. For each of the k times, you can choose a non-empty subarray that you haven't chosen previously. And then you choose an element inside the range that you chose with the highest prime score. Prime score is the distinct prime factors of x in the prime factorization. So prime factorization is go from smallest prime to biggest prime that is divisible to that certain number, and you keep defining the prime before you go to the next larger prime. For example, if we want to know the prime score of 300, and the first prime that we encounter is 2 because 300 is divisible to 2, so we define 2 and then we get like 150, and 150 is also can be divided by 2, and so we do that as well, and we will get something like 75. So 75 is not divisible to 2, and then you move to the next prime is 3, and you do this, and then you just keep doing until it reaches 1. So in that process, how many distinct counts that we have seen? We have seen 2, we have seen 3, we have seen 5. We have seen 3 distinct prime, so that's why the prime score of 300 is 3. So now we know what is the prime score. Back to the second point here. After choosing a subarray of LR, then we only care about that one element with the highest prime score. If there is multiple elements with the highest prime score, then we just choose the leftmost index, which is also the smallest index, and then we multiply the score by x. So that's pretty much all. So then we repeat it k times. It says at most k times, but it's almost certainly sure that we will want to do it k times because all of the numbers in the constraint are positive. So it's always better to times more than times less. So we're going to repeat these procedures k times and then return our answer. And the answer might be large, so we have to mod it as well. So let's take a look at the first example. Okay, so in this first example, the given nums is 83938 and k equals 2, and the answer is 81. Why? So let's take a look at what it looks like in the prime score for each element. So we know 8, if we do prime factorization of 8, it's just 2 times 2 times 2, and that's it. We don't move to the next larger prime because when we finish 2 times 2 times 2, it's already become 1. So that's why it's only 1 for the prime score. And for 3 is not divisible to 2, and then we move to the next prime, which is 3, and 3 is divisible to 3, and we do that, and 3 become 1, and we stop. It only has one element, which is 3, so it should be 1. So 9 is 3 times 3, which is also 1. And then 3, we already covered that, is 1. And 8 is already 1. We already covered that as well. So all of the prime score is 1. So what does it mean? So it says to get a score of 81, we can choose a subarray of 2 and 2. So basically 0, 1, 2, which is here, 2 and 2, we pick 9. So this one is 9. and 2 and 3 as well, because the first is 9 and the second is also 9, because when you look at this particular subarray, they both have 1 as the prime score. And if they have 1 in the prime score, then we can choose the left one, the leftmost one, which is also 9. That's why we can choose 9 again for this subarray. So this 9 comes from 2, 3, and this 9 comes from 2, 2. So they are coming from different subarray. So that's why we get this 81. So that's pretty much all for the example. Let's think about how can we achieve a solution. So the question says we can do K operation, and it makes the most sense that we just pick K largest possible. So, how are we going to multiply the element? We're always going to choose the element's values from these nums. So what I'm trying to say is that I want to know how many times I can use 9. I'm going to keep using it until K reaches 0, or until I cannot use 9 anymore. Then I will move to 8. And I will move to 8, and I will keep using 8 until I cannot use 8 anymore, or until I have uses all the K operations. If I use up all the 8, then I will move up to 8 here, and then I will move up to 3. So basically, I will just sort array. You can think of it like this, and then you just go from largest to smallest. So because when I can use 9, I wouldn't want to use 8. I want to use up all the 9 first, because the answer is the multiplication of all the chosen element, and all these elements going to be positive. So we always want to choose the larger element first, because it's always beneficial to choose 9 over 8 or 9 over 3 in any case, because we want to reach the maximum possible. But the question is, how do I know how many times this 9 appear? So previously we have calculated the prime score of each element. It's like 1, 1, 1, 1, 1. So all of them are 1. So if I want to use 9, how many times I can use it? So because it has prime score as 1, and also because if there is multiple same prime score, then I'm going to use the leftmost one. So you can see here is one time that I can use 9. Here is then another time that I can use 9. And here is also a time that I can use 9. So in total, I can use 9 3 times. So just to make the example output more clear, because K is just 2, and we can use 9 3 times. So immediately we know we're just going to use 9 2 times. And then 9 times 9 is just 81. So that's why we can just quickly come up with this 81. But we can use 9 one more time. For example, if K not equals 2, if K equals 3, then we will just do 81 times 9, which is I don't know what that is. Let me check. 81 times 9 is 729. So because we can use 9 3 times, which I have explained here. The first time is just itself, the second time is here, and the third time is here. So by the way, this one is not good, because when they are having the same prime score, I will choose the left one. So here, if I pick this particular subarray, then I will just end up choosing 3. So that's why it's not good. So after using up or the 9, then we're gonna go how many times you can use 8. Well, 8 is also very similar. So there's the first time you can use this, and then the second time is this. Or you can use this, and we can use this, and we can also use this. So it's 1, 2, 3, and then 4, and also the last one is going to be the whole array. So this particular 8 appears 5 times just for this 8. So, but we also need to consider this just 8 just one time. So in total, we can use 8 6 times. So you can imagine that if the answer, the k is not 2, is not 3, it's something like k is 9, then the answer will be something like 9 to the power of 3 and times 8 to the power of 6. Because we can keep using 8 for 6 times. That's the idea. We just try to keep using the largest possible value. And so now that we know how many times a certain numbers can be used conceptually, let's think about how can we calculate it algorithmically. So we can think like left boundary and right boundary of each index. So let's look again for our first example here. So for the prime scores array, it will be 1, 1, 1, 1, 5, 1, as we have mentioned a couple of times. So let's take a look at 9, how many times this 9 can use. So if we want to know how many times it can use, we must know the left boundary, meaning how far can I go to the left until I meet something that is larger than me. Because remember, if I meet something that is the same like this, then this 9 will immediately gone. So we can look at even longer subarray, but at the point that you reach this element from here, because they are having the same prime score and we are always choosing the smallest index, so we're never going to consider 9 again. So let alone something that is larger. For example, we made something like 2 here instead of 1, and we visit 2, and then we know that this 9 will never be used ever again for all the subarray that is in this direction after this certain element. So what I'm trying to say is that for the left boundary, you find the first GTE, means greater or equal. That is the left boundary. For each index, you just find the first greater or equal. That will be our boundary. And let's call it like x, and then x plus 1 all the way to I will be something that we can choose. Let's call it left length. That is something that we can use. It's for the left length. So for the right boundary, it's a little bit different but similar. We're gonna find first GT. This time is strictly greater. It's not equal. Because if it is equal, we can still do it. For example, here 1 is equal, and we should keep going to the more right because it is not our boundary. We can keep going right. That's why we need to find the first GT, or we reach the n, which is n in this case, where n is the length of the array. So for this particular 9, we know that the left boundary will be 0, 1, will be index 1. Index 1 is here because this is literally the boundary that we will hit. And the right boundary, there's actually no right boundary for this 9. We can go all the way to the end. So it's n. So the main idea is that there is a left length. That means that the subarray size doesn't matter with the subarray size on the right. The subarray size on the left doesn't matter with the subarray size on the right. So that's why when we have this left length, and we can also multiply it with the right length. And that would be how many times this 9 can use. And to calculate the first greater index or first greater or equal index, we can use an algorithm called monotonic stack, which is a pretty useful data structure in solving this kind of problem. There's an easier problem called next greater element 1 that you can practice it for. So in general, we're just going to use this monotonic stack to help us find the next greater element or the next greater or equal element in order to find a left boundary and a right boundary of each index. And after we having each boundary, we can calculate how many times does certain values appear, or how many times that we can use it in our calculation. And after that, we're just going to visit all the values that we can use from the largest to the smallest. And we're going to keep using it until k reaches 0. That's basically everything for the overview. Let's see how can we code this up. So first I'm going to initialize n as the size of the numbers, and I'm going to initialize the maximum variable as the maximum of all numbers plus 1 because later on I need to create every numbers using this like an array initialization length. And if I just used max number without plus 1, then I would just end up considering everything from 0 to maxi minus 1. But I want 0 to maxi, so that's why I have to plus 1 there. And for this flag, I'm just going to use it later for calculating the primes. So this is the mock in line 6. So its prime is initialized as first of every numbers at the beginning in line 7. So then I'm going to create a helper method to calculate a times b in modular. And in line 10 is going to be a power of b but in modular. So I won't go in detail for the implementation, but it's pretty straightforward. I just have to do the mock whenever I need to do the power operator. So yeah, basically if it is even, then we can just divide the power by 2 and then just calculate both of them recursively. So it's just something to calculate it efficiently, but this is pretty standard. So I won't go into details of the implementation of the multiply and power of the modular. So then I'm going to create a helper method called getPrimeFacts, which will take a number as an integer and return a list of numbers. So basically, I'm just going to return a list of the prime factors for x. So initialize it then as empty array. So if it itself x is a prime, then it's just going to return x because there's no prime factors other than itself if it is a prime. So then we're just going to do some boundary check. So if it is an even, then we just add the prime facts of 2 first, and we also check x divided by 2 is a prime. If it is a prime, then we add that as well. And then because we already considered 3, we can start from, because we already considered 2, we can start from 3. And then we're just gonna keep doing it until we are larger than the square root of x, basically. So if x mod I is not 0, basically x cannot be divided by I, then we're just going to ignore it and then continue. And otherwise, if it is a prime, then we will add these prime factors for this x. And if I times I is not exactly equals to x, it means that the other factor is not I as well. So we're gonna check if it is prime as well. If it is also a prime, then it's another prime factors for the x. And we're gonna I plus equal 1 to check for the next factor. And after all of them, we want to sort the prime facts because somehow we always want to go from the smallest prime factors first all the way to the biggest prime factors while doing the prime factorization. And then we're just going to return the prime facts for this get prime helper method. So then we're going to start from 2 all the way to the maximum of the numbers plus 1, basically inclusively. And if there's a flag, if the flag is marked as true, then we continue. And otherwise, we're going to mark this particular element as true. And then this is basically a technique to help us find all the prime numbers from 2 all the way to maximum. So this is a technique that can run in n log n. And I won't go into detail of this algorithm as well because it is like another problem, but this is useful for us to calculate all the primes under maxi. So then we're going to write another helper method, which is called prime score. We will also catch this so we don't repeatedly calculate the same prime score over and over again. So this prime score will just calculate the prime score that in the program description mentioned. So if it is a prime, then the prime score is only 1. Otherwise, we're gonna do some score calculation. So start at 0, and then we get all the prime factories. And then for each prime factors, if the current x is divisible to p, then score plus equal 1. And then we're just going to keep define x by p until it's not divisible anymore. And if we reach x equal 1, then we just break because there's no way that we can gain any more score after that. And that's how we're gonna calculate the prime score for a given x. So then we just want to store the prime score for each numbers for the given input array nums. And then we need an increasing stack to calculate the next greater element, as we mentioned before. So we also need to create a frequent of value. So basically, how many times we can use a certain value. That's what it is used for this array in line 54. So the right boundary for each element, and also the left boundary of each element. So in the worst case, the left-right boundary is just I, because at the beginning we don't consider any boundary at the moment. We're gonna calculate it now. So first we're gonna iterate everything from n-1 to 0. So in line 58, that's where we are going to calculate the right boundary of each element. So as we mentioned, we will use a technique called monotonic stack. So when this current score is larger or equal to the stack top, then we can just pop the stack top, because as we go to the left, then if we already have an element which is prime score I being greater than the stack top, remember the stack top is something on the right hand side of me. So they're going to be useless, because for anything on the left hand side, if they are asking for the next greater, they are not asking for this stack top, right? Even if they want to ask for the next greater element, then it will just ask for me, because I am greater than the stack top. The stack top is on my right hand side and it is smaller than me, so this is useless. That's why we can pop it, and then we can just calculate the greater boundary. So if there is no boundary at all, it's going to be n. Otherwise, we will just use the stack top as the boundary of I, basically the y boundary. And then we can calculate the y boundary here, and then also increase myself. And also include myself in the increasing stack. So then next we're going to calculate the left boundary now. We're gonna reuse the increasing array, but now I want to empty it first before we reuse it. This time we don't want to go from right to left, we want to go from left to right. And then we do the similar thing, but because the left boundary is different from the right boundary, so this time we only kill something that is strictly greater. If prime score I is strictly greater than the stack top, then I can kill it. And then we just calculate the boundary as well. So similar things. And then we have this left boundary. So then we can calculate the left length. The left length is just I, the current index minus the left boundary will be the left length. The right length is the right boundaries minus I. So basically we have left length and right length. And the frequency of these numbers will be plus equal to left length times right length, as we already discussed. And then we just still going to add this I to the increasing monotonic stack. And then we're gonna initialize our answer as 1. And for line 74, we're going to iterate every numbers in the given array, because that's what we can choose to multiply. But we want to reverse it, because we want to go from the largest to all the way to the smallest, not the other way around. And we want to know the frequency of this value, basically how many times we can use for this value. And then used means how many times will I actually use it, right? Because when the frequency is, for example, greater than k, it doesn't mean that we're going to use it frequent time. We're just going to use the minimum of k and frequent time, basically. This is used to be the exact number of times that this value will use to calculate our answer. So now that we know that value will use time, and then if we use the value use time, it's just value to the power of use, basically. And then we multiply that result to our answer and update it. And each time after it's done, k will minus equals to the use, because it used times. And on line 78, and if k is reaching 0, then we break out the loop. And if everything's okay, then we're just going to return the answer. That's pretty much all. Let's try to submit this. Okay, accepted. So that's all. Thanks for watching, and I will see you next time. Bye-bye.